Hey, Tom. Welcome to the Flume Horse.
Thank you.
It's great
Thank
to
you.
be able to sit here by the fire.
Yeah, it's great to be here
today. Well, what's been going on with you?
Well, one of my oldest daughter just got back from college at Purdue, so she's finishing her sophomore year, and so she's enjoying it there. And I was able to go back a few months ago. They had an event, and Synopsys brought some people out because Secretary of State Blinken went and some other government officials to talk about the CHIPS Act there, and Purdue's involved with that, and Synopsys is involved. So that was a good visit, and got to see a lot of things they have going on there.
Oh, that's great. Yeah. I have a daughter too, and she actually is a Flume Horse, and she were born at the same time in my life, and we acquired the Flume Horse in 2006, and she was born in 2006.
Yeah, that's right around the time I was getting into this industry at Luminescent. I was coming out of grad school. I was living in doing a postdoc at UT Austin, and then found out through my PhD thesis advisor there was a company doing this inverse lithography stuff. I didn't really know about it, but came out and have been doing it ever since then. Yeah.
Oh, wow, that's great. So you went 2006, and then I think you got acquired by Synopsys in 2012.
Yeah, about 6 years later, and I was I thought, oh, 6 years, like I'll never stay at another Synopsys for 6 years, and now I've been there for more than 10. So this just keeps going. It's an interesting field, keeps changing. It's interesting. I had a guy, a friend of mine I know, who's a lawyer, and he came up to me and he said, how can you guys keep working on trying to solve that same equation for so many years?
Same equation.
Yeah, and I said, if you think about it, the rough equations describing the whole OPC ILT problem are maybe kind of similar to how they were at the beginning, but all the parameters change and the problem gets harder and things change about it. So you're not able to just solve it. It's a continual process.
Yeah, you've been really successful at Synopsys, right? That you're now principal engineer. Like what's been like some of the reasons for your success? Would you say what do you think was your biggest contribution?
I mean. It's hard to say. Like I said, the problem is pretty difficult, and I think the fact that I just stick with it, and we've had a lot of people come in and out of the industry, and maybe leave to what they thought were greener pastures. But really, this problem is interesting, and there's government support coming now, and I think that really globally, this area has been really realized as something that is very important to different countries and nations and economies. And I think sticking with it and using the skills that I learned about math and applying them, and having an open mind to new techniques, and we'll probably talk about things like AI and machine learning. Being able to kind of understand those things and apply any available technique to the problem at hand has been something that has allowed me to stay involved and successful in the field.
So equation might be the same, but how you approach it from your point of view is changing, including deep learning and AI, right? Let's talk about that. So I know that you and your colleagues have published for a long time on using deep learning. Tell me a little bit about how you use it. Is it like for accuracy or for speed or other things?
Yeah, well, you can think at different levels. So one level is like at a very low level, we can try to replace some piece of the algorithm. For example, for the modeling and simulation, try to place some piece of the simulation with a deep learning method. So that's something you can do. And then there's also a little bit higher level, let's say, try to replace part of the ILT or OPC flow with a piece of machine learning, like a neural net, something like that. But then some really interesting stuff happens. We start getting into even a higher level, looking at things, like analyzing geometry or analyzing patterns or analyzing how humans use the tool. And so Synopsys has something called DSO.ai, and that's for kind of design space, but we're migrating that type of technique to the manufacturing space and looking for patterns and other things that maybe are not so intuitive in the tool. And as I mentioned, for human behavior or kind of learning programmatic things, some of the recipes, we call them, to make an ILT or OPC run successful are somewhat complicated. There's a lot of constraints and nonlinear optimization. And it's a question of, can machine learning actually help you learn how to put that recipe together in a better way? Not just to tune a parameter, but actually kind of structure the program in some way that it learns from previous experience how to do things in a better way.
So in some ways, it's the higher level thing, right?
Yeah.
How you use it might be improved
Yeah.
using AI techniques. That's interesting.
Definitely.
DSO.ai you mentioned, that's for physical implementation, right? And Synopsys just recently announced Synopsys.ai. It was IoT a part of that?
Definitely. The manufacturing tools and the math synthesis is all part of the Synopsys AI. We try to call it pervasive AI. So we're aggressively looking in any area of the manufacturing space we can to see where can we leverage gathering data, analyzing data, learning about the data, using machines and machine learning to learn about the data. So there's a lot of areas in manufacturing. Sometimes we used to think the tape out was sort of just the end of the process, but now we see it's actually the beginning. It's really in the middle somewhere, because there's a lot of tools in the fab, all of them giving out data, like petabytes of data, and we can gather that and we can analyze that data. And so, as you know, there's this concept of digital twin. So any tool in the fab that we can simulate is a candidate to build some digital twin. We build kind of digital twin of the scanner or something like that. But there's a lot of other tools. So if we can gather that data, there's a good chance for us to save money by running virtual experiments rather than physical experiments. And then we have a lot of things, monitoring process control and other stuff like that. And then after the chips are made, we actually have something called Silicon Lifecycle Management, or SLM. And this is kind of looking in the field. Let's say you have a chip goes out into a car or something. You want to understand really well, like, when is that chip going to fail? Something like that, and analyze it. So there's a lot of data they can harvest actually after the chip is manufactured. So we're talking both in the fab, upstream from the tape out, and then downstream from the tape out. There's a lot of areas where data can be gathered, and once you have big data, you can use AI to help analyze that.
Interesting. So, silicon lifetime management, how is that related to DSO.ai? I saw that DSO.ai has been really successful. There's been hundreds of chips or something, that's built using it.
Yeah. So I would say, the techniques and the ideas inside of DSO.ai, and I can't talk exactly all the details, but there is sharing across Synopsys of certainly ideas, but also software for the different tools to be able to say, well, this kind of piece has learned in one area how to analyze and optimize, and let's see if we can apply it to some other area. So there's a lot of sharing there, and Synopsys is really proud of being able to say we have pervasive AI and we have different groups learning from each other. In some ways, even that's kind of some meta learning, across the whole company.
So, but it's not like there's some kind of a central AI research lab or like a SWAT team that goes into different places and they're just AI experts. So it's not like that.
Yeah. So I obviously can't say exactly how the company's organized, but this idea of having AI experts and where do AI experts come from is interesting, because when you think about ILT, this is a problem where, or let's think about deep learning. Let's frame it from the deep learning side. Deep learning, what are you going to do? You're going to get a cost function. You say, oh, this is going to measure how well I'm learning something. And then you're going to have some unknowns, and you want to back propagate information or errors from your cost function back to all your unknowns and optimize them with some gradient-based method and say, let's make the unknowns better so that we can predict what's actually happening. Let's learn from our data. And if you ask me to say, can you describe ILT without talking about lithography, I'd basically say that same exact sentence about how to describe ILT. So you have cost functions. You try to measure things on the wafer. You have unknowns, which in our case, we have a model that's fixed, but we have the mask edges. Full chip mask edges is all a bunch of unknowns, or we can consider, mass transmissions or other, however we want to represent the mass, level sets or other things. So really, if you want to frame it that way, you could say ILT's been doing deep learning the whole time. And so what that means is we already have experts who really understand the fundamentals of machine learning and deep learning in some very deep way. Now, there's always new things coming, right? We're going to say, oh, there's some new neural network coming, or there's some new idea that some of these, the great thing about all this machine learning is there's a lot of open source contributions, and the big companies like Google and other places will really put things out there to make it easy for everyone to use. So there's always new ideas coming from anywhere, and we have taken the effort to find some experts, from different industries that are not from the lithography industry. Like, I never came from the lithography industry, but I'm able to learn it and apply my skills to it. So we're doing the same sort of thing. Find some people that have some expertise in learning that may be unique and may be different than what we have, and learn from them. So there's a combination of having the understanding that we already had for years about this type of optimization and learning problem, and also getting help from externally. And then across, like I mentioned before, sharing across the entire company at Synopsys.
Yeah, that's pretty good. Yeah. That's really good. But another area where there might be a difference in how you approach it, even though the same equations are being used as GPU. You recently announced that you're going to be doing some GPU-based computing. What's involved in that? And
Yeah, so we did have a press release with a partnership with NVIDIA and TSMC and Synopsys talking about using GPUs to accelerate OPC. And that is definitely something that we worked hard on, and we're moving in that direction. And one of the interesting things, there's a couple interesting things there. One is you know about machine learning being used for GPUs, and say, oh, if we have a convolutional neural net or other image processing techniques, it's real easy to migrate because it's parallelizable. We can migrate to GPU. But actually, for the mask making space, there's a lot of polygons. We communicate the data in polygons at the end of the day. Data comes in polygons, data goes out. That's a little bit harder to get accelerated on the GPU, not traditional thing that would be accelerated. So there's a lot of work we've done, and NVIDIA has done, to help make sure that that can be a reality. And the second thing that's really important is making sure that when you have a cluster that's mixed with GPUs and CPUs, that you actually can get optimal efficiency and usage and loading of all those compute units at the same time. You don't want to have something where the CPU is just there doing tons of work and the GPU is waiting and it does a little bit of work, or the GPU is doing all the work and the CPU is not doing anything. So this kind of loading in this mixed environment is really critical, and I think it really helps to have both TSMC as the fab, NVIDIA as the hardware provider, and Synopsys as the EDA tool working in concert to make that a reality.
Ah, that's good. That's interesting.
Yeah.
So you think GPU acceleration is in general in the future of what we do?
Yeah, I think it's definitely heading that way, and it's a candidate. So one thing I can say is, going back to the luminescent days, we had a project there which was to use some FPGA chips to try to do some acceleration. This is probably in the spirit of GPUs in some way, with custom code that could be accelerated there. And eventually what happened was the CPUs just kept getting so fast that it was just like we couldn't keep up. Now, we do have, on the GPU side, NVIDIA pushing really hard. And Jensen Huang's talking about, the new scaling, the new type of Moore's law of scaling of GPUs. And I think they're going to work really hard to continue growing that. And that's going to be a real strong tailwind to help push us towards success in that area. But it will, like I said, the complicated thing will be, how do you load up these GPUs? And there's also other things, right? There's other competing hardwares that are going to come, like TPU or other things. You never know which one's going to be successful. So you kind of have to make sure you're keeping track of it and partnering with the hardware vendors and pushing towards all of the variable solutions that are out there. Right, and that actually adds a lot of work, but that's okay for us. We're growing, and we need to have more engineers. And I think all of these candidates. This is another reason that this field is really exciting for people is you can use any technique that's out there in the world, because it's such a hard problem. Yeah. Like any kind of computer or algorithm could be applied and make some success.
Yeah, yeah. Let's talk about curvilinear ILT.
Okay.
Right? In 2017, actually, yeah, you gave what I thought was the best talk of the decade at the eBeam Initiative event.
Thank you.
That talked about curvilinear IoT, and in fact, 2017, we weren't sure about EUV yet, right? But yet, what you said was that curvilinear IoT is the way EUV IoT ought to be, and you explained why, and you showed some data. I think that was the first time anybody said that publicly, and it sure turned out to be true, I think.
Yeah.
Tell us a little bit about curvilinear IoT, where you started.
Yeah, I mean, back then, and even far before that, ILT was already being used for the VSB writers. Like, if the economic equations or return on investment make sense, they could make a Manhattanized or rectilinear ILT mask, and it's still being done today. And the thing that the curvilinear allows, especially with the multi-beam writers and now the more industry-wide acceptance, let's say, of the new multi-gon Oasis format and things, it allows us to put curvilinear into other areas that maybe even aren't the most mainstream. So now we can have something that we call curvilinear OPC. So this is that we don't need it for the most advanced node, but if the curvilinear mask can have an advantage because it's less constrained, the MRC is easier to meet, et cetera, that can be something where more nodes and more customers can have access to using the curvilinear correction tools. And so that's a really great thing that it's not just ILT anymore. ILT can definitely do it and is using it, but also we can do it with OPC.
But also for the advanced nodes for EUV, isn't it more and more curvilinear, or what do you predict is going to happen in the future?
So, I mean, for the future nodes, the thing about curvilinear and EUV is always going to be some return on investment equation. Like, for not everyone has a multi-beam writer. That's one thing, right? So even if you do have a multi-beam writer, you can say, well, if I make this mask, how many wafers am I going to make? Let's say you make X wafers with some mask. But somebody else might say for a different style of chip or different use case, they might make 1,000X wafers with that same mask, right? So you can amortize the cost of making that curvilinear mask over a different amount of chips, and that's going to change the equation of when is curvilinear and even EUV appropriate for certain things. Now, let's say we decided, all right, VSB, multi-beam writer, it's all the same cost. Then it's a question of, all right, is the curvilinear just better than the rectilinear? And the answer, I think, is yes, because it's less constrained. Like we talked. Yeah, for the wafer, it's less constrained. The mask rules are easier to meet, and it's just more natural. The curve shapes are more natural. Then the second question would be, all right, if that curvilinear mask is better, are you going to be able to actually get to that curvilinear mask? So then it's a question of the EDA tool. So this is where Synopsys, and I think the industry-wide, is really investing in, can we make sure that curvilinear shapes, the file size is not too big? Can we agree on what the MRC is? That sort of thing. And I think Synopsys, like I mentioned, with the ILT and OPC, is really pushing hard in that area to allow curvilinear to be more friendly and more manufacturable. And now for ILT, it used to be that we would just say, well, maybe we can use it for a hotspot fixer or a memory array, something with high repetition, or like the hotspot fixing, maybe something that has a low total area that needs to be processed on a chip. But now, because the scanners are Moore's law keep going, and the scanners aren't changing that much, ILT is really becoming better, and we're making it faster, especially with things like GPU, machine learning, that we can expand ILT to full chip runs, and that's what we're doing working with our customers. And we have things like, we call it target optimized ILT, where it's actually kind of changing the design, spreading things out and moving them during manufacturing. So a lot of advanced techniques that actually can be done on a full chip level. And that's really great for ILT. And as far as going back to the rectilinear versus curvilinear, if you think about it, rectilinear shapes, while they're easier for us to understand, like, oh, okay, this table's a rectangle, like, oh, I understand how to make it, right? But in nature, light's not moving in a rectangular way. It's moving in a smooth way. So if you think about, for AI, it can learn things. For example, ChatGPT is a humongous computation. It takes so much money to train it, right? Because it's working with a human construct like language. It might seem natural to us, but compared to just wavelengths of sound, human language is maybe not so natural. It's very structured, and different languages are structured a different way. So it took them many, many years and humongous models to try to learn some concepts about language. But if you think about image processing, the convolutional neural nets, with a much, much smaller model, they're able to identify many, many things in pictures and do almost magic.
Because it's more natural.
Because it's more natural. So I think if we can think about it in that way, it's very likely that AI can actually do more with the curvilinear shapes and the curvilinear representation than trying to force it to be in this rectilinear space.
Oh, that's a really interesting perspective. So even though ChatGPT uses huge amounts of computing, maybe trying to do IoT isn't the same kind of degree of complexity, right? EUV does make it more complicated, right? Because EUV requires more resolution, so, more pixels, so you have more to compute. And you have also the through slit variation for EUV that 193i doesn't have. So EUV computation is more complicated, right?
I mean, it's definitely, so as far as EUV computation goes, it's definitely more complicated and more intensive, but it's not quite as intensive as you could say the ratio of 193 to 13 nanometer wavelengths. It's not just like, oh, we just say this thing is 15 times more complex, right? Because there's some complicated thing about how much of it can be done in pixelated space versus some polygon algorithms, and the design sizes are shrinking, but it's not shrinking in like 15 times or something like that. So that's an interesting area. Another thing is, the EUV of today is not the EUV of 10 years ago. And what I sort of mean by that is the problems that we discussed for DUV some years ago, saying, well, maybe can I use ILT with the DUV to replace going to double patterning? Now those questions are relevant for EUV. So all the tricks and tools we have are going to have to be used. And then second part, you're talking about the slit variation, through the slit. Yes, there is variation. And, if we think about the history or evolution of all the mask synthesis tools, first you might have started where, well, the mask is the same as the design, and that worked. Then you need to add some rule-based sizing, and said, oh, cool, people said this is going to be really complicated. We need to write rules, etc. Then they went into model-based and said, oh, we don't even know how to make a model. So, and then they have rule-based assist features, then model-based assist features, then ILT where you have main features breaking and merging with the assist features. And each time there's a progression down that path towards a more sophisticated solution, there's kind of more ambit or range of effect which you need to quantify that's larger, and you need to model it and you need to account for it. So going to the slit, yes, it's larger, but I think we're going to be able to handle it in a way that is computationally let's say, sophisticated and not as naive as saying, well, if you have the slit, that means every contact you have on the layer is solved completely differently. I mean, yes, they do get different masks at the end, but ultimately the slit variation is not the main effect that is being captured. So we're able to exploit the repetition that the chip has regardless of where the patterns are in the slit. And so we can take advantage of that. And the EDA tools will always find some way to take advantage of the repetition it can find, even if you think, well, that's not the most appropriate way, but we'll find a way to use it. Yeah.
That's part of the creativity that goes into same equation, but very different implementations, right?
Yes, definitely. That's what we talked about at the beginning. Yeah.
That makes it really interesting.
Yeah.
So the resulting EUV masks eventually, but maybe not at 3 nanometer, but eventually is going to be different shapes everywhere, right? So it's not like you can just use hierarchy, but like you said, you would exploit hierarchy.
Yes.
Take advantage of it, but it's not exactly just repeat.
Yeah, it's definitely going to be different. So on the output, you're going to look across the slit and things are different. And that's the downstream tool will have to deal with those differences. But definitely during the mass synthesis part, there's repetition which we can exploit to try to reduce the computational burden so that we don't need to solve those things just so uniquely.
Yeah.
And maybe even we can pass information to the downstream tool, and that could be used. That's another area to think about.
So, this complexity of computing, basically people say everything in UV is more expensive, and that's no exception in IoT, it seems like. But does deep learning help with that? Like, do you think deep learning is going to be an essential part of IoT going forward?
I would say deep learning probably already is an essential part of IoT.
Okay.
We talked about the different levels where deep learning can be applied. At a low level, for example, replacing a small algorithm; to the mid-level, replacing some part of the ILT flow; to the higher level, modifying the recipe or trying to figure out how to tune parameters that are sort of unwieldy or non-intuitive. So that's definitely an area. And with GPU coming, something that is very well, a big driver of GPU and very well suited for GPU is machine learning algorithms. Without GPUs, I don't think we would be talking about machine learning. We would be like 20 years ago saying, this is something interesting, but it's not really practical. But now with the GPUs, it's very practical. So if we can take part of the ILT flow, or as much of it as possible, and migrate to something like a machine learning model, which is already very friendly and well known to be accelerated on the GPU, then we can exploit that GPU even in inferencing and get really big computational gains there.
Yeah, so tying it all together, GPU, deep learning, auto computation, same computing, but a lot of different, stuff, and the problem gets harder and harder and harder. But really, when you started 2006, right? You had this equation in mind. You got into it, and then you changed companies, by acquisition to Synopsys in 2012, and then you did your incredible presentation in 2017, and what you said all along has turned out to be true, right? It's exactly what's happening, and even many years into the future, it looks like what you turned out to be right.
Yeah, it will be interesting to see what happens going forward. I probably wouldn't imagine that we could have something like machine learning that could do all the things it does. And another big thing that's happening now is the government spending and the real importance, like we talked a little bit earlier, that all the countries realize this chip manufacturing is a really important national security type thing. This is going to really help the industry and give it more attention, and hopefully get more smart people coming over and really realizing that this is an important and interesting problem to work on, as I have found over the years.
That's great. Very, very, very impressive. Thank you very much.
Thank you, Aki. Yeah, it's been a pleasure to be here.
Yeah,
this is really interesting to talk to you.
That's really great.
Yeah, thank you.